So today we have Dr. Meiyun Lin virtually visiting from GFDL in New Jersey. Dr. Lin got PhD from University of Tokyo. And then after that, she moved to the US, at first in Wisconsin, to work with Tracy Holloway. After that, she moved to GFDL, then conducted research focusing on the intersection between air quality and climate. So she's gonna talk about her most recent research. Currently, she is a research physical scientist at the GFDL. So without further ado, Meiyun, please take the floor and then give us a seminar. Thank you.
Okay. Hi, everyone. Thank you, Professor Kim, for very nice introduction. And thank you all for tuning in and giving this opportunity to share some thoughts on Earth system feedbacks to air quality extremes in a changing climate. So with rising temperatures and shifting rainfall patterns, compound drought and heat waves are increasing in frequency and intensity. High temperatures accelerate soil drying, and dry soils warm the atmosphere by retaining less water for evapotranspiration. This process can be operate on hourly to daily time scales, but it can also be interpreted in the context of climate change, where increasing temperatures increase atmospheric evaporative demand and also change precipitation patterns. Recent hot drought has caused severe impacts on both natural and human systems, including mass loss of life. For example, in California, higher temperatures and drought are increasing the frequency, intensity, and extent of wildfires, causing severe air pollution and property damage. The 2011 Texas drought caused 8 billion agricultural loss. Thousands of acres of corn were destroyed. Oh, I have difficulty moving. Okay. And the 2012 Central US drought caused 35 billion agricultural loss in the Midwest. Over Europe, drought-induced tree mortality were measures during the 2018 Central European drought. And epidemiological studies suggesting that it's not just extreme heat, but also poor ozone air quality contributing to tens of thousands of deaths during European heat wave and drought over the last decade. So how does air pollution respond to heat wave, drought, and Earth system feedbacks in a changing climate? There are several key processes, especially the drought conditions accompanying heat wave. How drought conditions accompanying heat wave influence air quality is poorly understood. High temperatures leading to accelerated chemical reactions and increased emissions of ozone and aerosol precursors from the biosphere. Air stagnation leading to contribute to pollutant accumulation. Drought causing reductions of ozone removal by vegetation. Under severe drought stress, plants close its system model to conserve water, consequently limiting the ozone uptake by vegetation. The extent to which this process contributes to increases in surface ozone concentrations is poorly understood. owing to the lack of process-based model formulations and long-term ozone flux measurements. On decadal and centennial timescales, CO2 fertilization, anthropogenic land cover change, and shift in plant species due to adaptation can not only influence emissions from land, but also pollution sink to land. For example, with rising CO2 concentrations, plants grows better and better. So stomata does not need to open that much for the equivalent amounts of CO2 transmission. These processes can reduce ozone uptake by vegetation. So biosphere-atmosphere interactions are complex. Many and sometimes offsetting factors could be in play. So challenges in understanding Earth system feedbacks to air quality includes the lack of long-term, especially multi-year and decades flux measurements over various types of terrestrial ecosystems, the lack of interactivities of atmospheric chemistry with land atmosphere in current Earth system models. For example, the widely used Wesley dry deposition scheme does not account for stomata closure under soil drying or elevated CO2. Atmospheric chemistry in semi-6 models are not coupled to inactive wildfires. And there are also large uncertainties in modeling emissions from land biosphere, such as challenges in representing wildfire occurrence, spread, duration, and emission variability in individual fires. Model challenges in accurately simulating hydroclimate variability and representing heterogeneity in land surface atmosphere coupling, both are critical for assessing vegetation feedbacks. So in my talk today, I will talk about my research at Princeton and NOAA GFDL, hoping to address some of these challenges. So I believe we need process level understanding across time scales from days to decades and from global to urban spatial scales. So I will divide the talk into 3 parts. First part will focus on roles of drought stress vegetation on observed ozone air pollution extremes and trend. So from the 1960 to 2018 over Europe. The second part, I will talk about Western US particulate pollution from wildfires under 21st century climate change. Then I will briefly introduce a cross-division effort at GFDL to build a variable resolution chemistry climate model, specially designed for research at the nexus of US climate and air quality extremes. So jump right into the first part. So this will be based on a paper we recently published in Nature Climate Change. We find that we highlight a previously underappreciated climate penalty feedback mechanism as a missing piece of the puzzle why European ozone pollution is persisting in recent decades, despite stringent controls on regional precursor emission change due to regulations. So you can see that trends of ozone shown as gray and black dots in the top panel does not mimic the trends of NOx and VOC emissions shown on the bottom 2 panels. Emission remains almost constant in the 1980s, followed by a sharp decrease to as low as 1960 levels by 2020. Unfortunately, summertime ozone measures in Europe increased from the 1980s to the 2000s, even trending up over the last decades, correlating with rising surface air temperature. So the ozone temperature regression slope is 4 to 5 ppb per K, which is often referred to as the climate penalty factor. Despite decades of research accurately simulating the observed ozone trends in Europe, remains a serious challenge in various models, including even models driven by historical emissions and observed meteorology have difficulty simulating the observed ozone trends, indicating an unknown climate penalty feedback mechanism. So embedding an inactive ozone dry deposition scheme into GFDL Earth system models help us solve the puzzle. In contrast to the widely used Wesley scheme, our model includes mechanistic simulations of ozone deposition to vegetation, responding dynamically to photosynthesis, soil water availability, vapor pressure deficit, and atmospheric CO2 concentrations. The model has been carefully evaluated against available ozone flux measurements around the world. And for more model details and evaluation, I encourage you to read my 2019 Global Biogeochemical Cycle paper. So long-term ozone flux measurements are very limited, but required important to evaluate modeled interannual variability. So we were able to find some data sets to do this. So here are comparisons of observed and modeled reductions in ozone removal by forests during over bottom forests in southern Canada during the 2012 drought. And here's comparisons of reduced ozone removal by vegetation over a Danish forest during the 1992 summer drought. So the middle panel are observations and the right panels are models. And similarly, this is comparison over an Italian forest during the 2003 drought versus the 2004 wet year. So middle panel is observations show that severe drought stress during the 2003 events caused 50 to 70% reductions in ozone deposition velocities. And the right panel is model, so they are broadly consistent. So evaluation like this give us some confidence that this model is capable of simulating the response of ozone deposition to drought. So now we rely on the land model driven by observed precipitation and observation-based atmospheric forcings to examine how ozone deposition rates over Western Europe has evolved with climate during the past half century. So the green lines here shows models daytime ozone deposition velocities average over natural and secondary vegetation. So you can see that it varies strongly on interannual to decadal time scales, correlating with drought events shown as bars. Since 1980, there is the model suggests a 6% per decade decrease in ozone deposition rates over Western Europe, attributed primarily to soil drying over the past 4 decades in Europe. And we also look at the influence of land cover change. So here you're looking at land cover in Europe, looking at the 2000s minus the 1960s distributions, fractions of different vegetation type. So you can see that the secondary lands grew substantially, resulting from natural wood harvesting and abandoned agricultural lands. Conversions of natural lands to secondary vegetation will lead to increases in ozone deposition velocity, and conversions of croplands to secondary forest will lead to conversions of natural lands to secondary vegetation will lead to decrease in ozone deposition velocity, and the conversions of croplands to secondary forests will lead to increase in ozone deposition velocities. But we do not, they offset, and we do not find substantial influence of land cover change in trends of ozone deposition rates over Europe. Instead, reduced stromatal conductions by natural and secondary vegetation under drought stress plays a dominant role in shaping year-to-year variability and trends of ozone deposition rates over Europe. Although CO2 fertilization is found to cause reduced stromatal conductance in future climate, as suggested by climate models, and we find that these effects has not yet emerged during our 60-year study period in present-day climate. So we also look at the influence of biogenic isoprene emissions. So the model suggests increased biogenic isoprene emissions due to heat stress of the vegetation. And this is based on Meiyun 2.1 in our model, which does not account for the effects of drought, CO2 fertilization, CO2 inhibition, and anthropogenic land cover change on isoprene emissions. And some of these effects are offsetting, and it's kind of difficult to judge on what are the net impacts on isoprene emissions during these study periods and during the episodic heat wave and drought events. So a frequent asked questions is the relative importance of reduced ozone removal by drought stress vegetation, increase BVOC emissions due to heat stress, and reduce BVOC emissions due to drought stress. It's difficult questions, but I look at observations at Hohenheisenberg sites in Germany. So this is you are showing that scatter plots of temperature and isoprene concentrations. So you can see that isoprene concentrations show positive exponential correlations with temperature. So suggesting that perhaps the heat stress induced isoprene induced increases in isoprene emissions are more important than drought-induced decreases in isoprene emissions. So perhaps these factors impact the long-term trends, but I don't believe that on interannual time scales that the model is too off. I think the interannual time scale, the model is probably about right. So now look at the impacts on surface ozone pollution. So here you are looking at anomalies in July mean MDA ozone concentrations at Hohenheisenberg, Germany for 1960 to 2020 from observations in black. So the blue curve shows the model with ozone deposition held constant at 1960 levels, but with varying biogenic isoprene emissions and varying anthropogenic emissions. So now you can see that this blue model have difficulty simulating high ozone anomalies during heat wave and drought. So you underestimate the observed ozone anomalies by 10 to 15 ppb. And the red curve is the model with ozone deposition varying with climate and vegetation states. So you can see that it better simulate high ozone anomalies during heat wave and drought, and also better simulate the observed ozone increase in the most recent decades as compared to the earlier period. And the orange curve is the model with varying ozone deposition velocity, but under 1980 high NOx emission conditions. So the emissions are held constant in time during in the orange model. So you can see that this orange model show a correlation of correlation R squares of 0.6 with observations, indicating that climate variations played a dominant role in shaping interannual to decadal variability in ozone air pollution over Europe. Reduced removal by drought-stressed vegetation worsens ozone air pollution extremes, as demonstrated here, showing daily max MDA ozone concentrations, probability distributions of MDA concentrations from observations in black, and a base model with ozone deposition held constant in blue, and the new model in red with ozone deposition varying with climate. So you can see that accounting for reduced ozone removal by drought-stressed vegetation leads to threefold increase in simulated high ozone events above 80 ppb, which is significantly larger than a 60 ppb European target for protecting human health. And also, vegetation feedback exacerbate climate penalty on ozone air pollution extremes, increasing the sensitivities of ozone extremes to increasing temperature. So the observed climate penalty factor is highest in densely populated regions over Western Europe. And then the middle panel is the model with ozone deposition held constant at 1960 levels. So you can see that it substantially underestimates the observed climate penalty factor. And with ozone deposition varying with climate, the simulated climate penalty factor increased by 20 to 30%. So these, and comparing the top and the bottom two panels, you could see that emission reduction accomplished through current legislation alleviated the climate penalty, the ozone climate penalty. But even stronger emission controls are needed to achieve a targeted levels of ozone air quality in the coming decades, as events like 2003 drought are projected to become twice as frequent in a warming world. Published literature largely argue that regional anthropogenic emission reductions play a dominant role in shaping future ozone air quality. I believe we may be a little too optimistic because these earlier models do not include Earth system feedbacks as we talk about here. So I think Earth system feedbacks, particularly land biosphere feedbacks during drought, are central to determine air pollution extremes and thus need to be considered when designing an effective clean air policy in a warming climate. And to gauge the relative impacts of emission change, Earth system feedbacks, and climate variability, I think we need a model to be able to reproduce the observed ozone temperature relationship, drought temperature feedbacks, and a lot of and also have sufficient high resolution to resolve urban scale structures. As you can see here, that the model underestimates the observed climate penalty over the air basins over northern Italy. And this suggests, so as I will come back to this point, that we need a variable resolution model for seamless assessments of global dimensions to urban air quality. And now I'm moving to the second part, increasing wildfire activity in US west in future and climate. And CIMIC 6 model, Earth system models suggest a substantial increase of fire CO2 emissions in a warming climate. So I'm showing you here CESM2 projections for the different shared socio-economic pathways. Then you can see that a substantial reductions in soil moisture under the extreme SSP 8.5 scenario shown as red. And so rising temperatures and soil drying combined with increased biomass due to CO2 fertilization leads to substantial increases in fire CO2 emissions. So fire CO2 emissions almost double to triple under SSP 8.5 and also under SSP 4.5. So unfortunately, CIMIC 6 chemistry climate models, atmospheric chemistry, as I said at the beginning of the talk, atmospheric chemistry in CIMIC 6 chemistry climate models are not coupled to inactive wildfire emissions. So these chemistry climate model simulations use prescribed wildfire emissions, accounting for land use change, the impacts of land use change only, but not accounting for impacts from climate change. So this is a mean PM 2.5 average over the Pacific, US Pacific Northwest, simulated by CIMIC 6 models. So you can see that it does not change much across the course of 21st century. So we have to develop an empirical statistical model to describe the relationships of PM 2.5 at a given location to regional fires and meteorology. Then we feed this model with change in wildfire emissions and climate projected by CIMIC 6 Earth system models under a suite of shared socio-economic pathways. So these are results shown as these lines. So you can see that under a low mitigation scenario, that is SSP 8.5, with CO2 emission triples by 2075, mean PM 2.5 pollution in the US Pacific Northwest almost tripled by the late 21st century. And this increase is reduced to 40% under SSP 2.6 with CO2 emissions cut to net zero around 2075. So these spread across the scenarios highlight the co-benefits of climate mitigation policy on air pollution by changing particulate impacts, particulate pollution from wildfires. Large wildfires burn across the Western US in 2017, 2018, 2020, and also 2021, caused severe air pollution, property damage, and loss of life. The fact that these events occurred in short intervals, just over 5 years, and 4 extremes over these 5 years, may indicate that climate change is already driving significant change in fire regimes. So in the paper, we try to understand how these events may change in future climate. And we apply extreme vary theory analysis to understand the probabilities of 95 percentile PM2.5 at Western US, exceeding the 35 microgram per cubic meter US air quality standard under these different scenarios, and also trying to understand the return periods of 2020 particle pollution extremes from wildfires. And you could see that these gray lines is all historical observations, and the dotted lines is observed extremes during 2017, 18, and 2020. And the red curve is the exceedance probability under the SSP 8.5, and you can see that it remarkably resembling the distribution for these consequential recent extremes, indicating that these extremes become a new norm by late 21st century. And for the return period, these extreme events, return periods of these extreme events decrease from 20 to 25 years in present day climate to 3 to 5 years under SSP 4.5 and 8.5. Okay, so now move to the last part of the talk. So as I said, we were able to understand the impacts of wildfires on PM pollution over the Western US under future climate change scenarios. Is because of the relationship between wildfire and PM pollution is relatively straightforward compared to the relationship between wildfire emissions and ozone pollution. So the impacts of wildfires on ozone pollution is more complex and depending on scales, especially as human population move into more fire-prone regions. The wildland-urban interface may become increasingly important in assessing fire impacts, especially mixings of organics from wildfires, volatile organic compounds from wildfires with knock-rich urban pollution may be decisive factors in determining ozone air pollution, triggering ozone air pollution exceedances in urban areas. So just to give you an example, the right panel here, the animation showing that the severe ozone pollution caused by mixings of smoke with urban pollution and associated hot and drought conditions during the 2020 August, when a lot of fires occurring here. So you can see the cross indicates the presence of smoke, and this is shaded squares indicating ozone pollution, with this dark red indicating the ozone pollution exceeds the 70 ppb EPA limit. And another challenge is that, so this is a kind of scale aware issue. We need to think that mixings of wildfire emissions with urban pollution creates ozone pollution in cities, and also accurately representing land surface heterogeneity is becoming critically important in Earth system models. So considering all these effects, we need a high resolution model to better address, better understand global dimensions to US urban air quality in a changing climate. And to addressing these issues, I'm leading a cross-division effort at CFDL to build a variable resolution chemistry climate model, specially designed for seamless assessments of global dimensions to US urban air quality across time and spatial scales. The model has horizontal resolutions of 12 kilometers over the continental US, allowing it to see resolve cities, mountains, valleys, and urban to rural chemical regimes, and heterogeneity in land atmosphere coupling processes, with the resolution gradually reducing to 100 kilometers. At the other side of the globe, we achieve computational efficiency needed for large ensemble simulations and centennial scale projections. So the model is built upon stretch-grade versions of the GFDR FV3 cubisphere dynamical core and CIMIC-6 and AM4 global chemistry climate models contributing to CIMIC-6. So we are not only increase model resolution, but also trying to increase coupling and interactivities of atmospheric composition with land biosphere. For example, the model will include a dynamic urban canopy model to allow assessing the impacts of urban heat islands on ozone air quality in cities. And the model will include inactive dry deposition to land. As I show, it's important to assessing ozone air quality in a future climate. And the model will also include inactive dust emission from land, which will allow us to study the impacts of drought on and wildfire burned areas, like burn scars on land cover change and PM air quality. And we are also working on implementing a dynamic smoke plume rise based on satellite observations of fire-ready power. And this will allow us to better simulate the downwind impacts of wildfire plumes on urban air quality. And over the long-term goals for the model includes inactive photosynthesis-based BVOC emissions from the land, and also inactive biomass burning emissions from land. So there's a lot to work on, but this is kind of a dream model, and I'm very excited to have first publication coming out very soon. So some initial results to show you. We start with evaluating precipitation. So the qualities of model simulations of precipitation reflects the overall qualities of the model, because precipitation affects global circulation patterns, temperatures, relative humidity, and a lot of other things relevant for air quality. So the overarching goal is to have marked improvements of storminess over the continental US, along with a good simulations of global scale circulation and climate comparable to our 100-kilometer model. So I'm showing you simulations of annual mean precipitation over the Western US from observations on the left, and the middle panel is our 100-kilometer model, and the right panel is our stretch grade variable resolution model with 12-kilometer resolution over the continental US. So you can see that the stretch grade AM4 show remarkable ability in simulating precipitation patterns over the Cascades and over Sierra, and also the LA basin, broadly consistent with observations. And the model Also, the stretch-free model also reduce the precipitation drive bias in the coarse resolution models, and these biases presence in many climate models are difficult to simulate. So we are able to simulate these features better. And then there are some challenges, such as substantial shift of precipitation to large scale, from convective precipitation to large scale, which are expected at higher resolution models. But sometimes we find that these cause model deviation from the observations. Okay, so as you can see, these better simulations of precipitation and hydroclimate variability will have significant implications for model simulations of fire weather, drought, vegetation states, and feedbacks to air quality. And we are getting to evaluate the model simulations of PM and ozone over California. So you could see that the models show substantial ability to simulate winter haze in California's Central Valley. So, this is observations, and this is 12-kilometer variable resolution model. And this is the middle panel is 100-kilometer model. So you see nothing in this 100-kilometer model. And here are comparisons of model simulations of summertime ozone pollution over the US West. And this is observations. The middle panel is a 100-kilometer model from the CIMI-6 archive. And then right panel is the stretch-gray model. So you could see that the stretch-gray model is capable of simulating many detailed spatial structures of ozone air pollution across the US West, such as relatively clean air along the coast and heavy pollution in Central Valley and also Southern California. And there are some issues. You could see that the model is bias high in Northern California air basins. And we are looking into this and find that some of these biases may be due to too coarse land cover currently used in the model and issues in the biogenic isoprene emission map. So I'm really looking for high resolution isoprene emission maps for trees, crops, and shrub and grass currently implemented in Megan 2.1, and also looking for isoprene flux measurements to evaluate the model. And don't forget that this stretch-gray AM4 is a global model. So we are able to see these fine scale features like those in regional model, but placing these fine scale features in a global model allow us to investigate global climate feedbacks to US urban air quality, and also take into account the impacts of long-range transport and stratospheric intrusions and a lot of other things in kind of a coherent structure. So these avoid inconsistencies associated with imposing global model boundary conditions in regional models. Okay, so finally, some final thoughts on Earth system feedbacks to air quality in a changing climate. So I think we need long-term multi-year ozone and isoprene and major monoterpene flux measurements over representative ecosystems at northern mid-latitudes. And in my mind, I mean, as a young modeler, I think doing these long-term multi-year measurements at representative sites that can see the influence of large-scale conditions are more useful in terms of evaluating model, particularly interannual variability, than doing like campaign a few days here or a few days there. So this is just my perspective as a modeler. And I think we also need a process-oriented model evaluation, not only for mean state, but also looking at interannual availability and focusing on how well the model represents the response of air quality to meteorological drivers and climate drivers. And finally, I think we need large ensemble projections to gauge the relative impacts of climate change, regional anthropogenic emissions, and climate variability. With that, I will stop here. Thank you.
Thank you very much. Thanks for the very interesting talk. If you have any question, you can unmute yourself, ask questions, or leave your question in the chat box, I guess. So there was one question I could probably, this is logistics, asking about the access to the recordings. I think Elliot might have some depository something, but it may not be open to public, but I think you can ask. So I will ask about that. That's my understanding. If Elliot's still in the room, you could unmute yourself, and then how can we can access that? And maybe she's not here. Okay, Jane, go ahead. You can unmute yourself and ask a question.
Sure. Hi, thank you so much for the great talk. Two small questions. One is, when you're showing the map of the pollution created by changes in wildfires, the change seems to be focused in the Pacific Northwest, which it wasn't necessarily obvious to me that that's where it would be focused versus like farther south in the West. I'm just curious if that was expected or why, if there's just a lot more stuff to burn up there.
So this is primarily driven by change in wildfire emissions projected by 3 Earth system models we use there. And I don't want to say this is a robust response because we have 3 models, and one model show that the Pacific Northwest is really a hotspot, but one model show it's not. So in terms of north to south gradients, I wouldn't make too serious in terms of this hotspot. But the model that suggests this is like warmer temperatures and drying soils in this area.
Cool. That's very interesting. Thank you. And my quick follow-up is this supermodel you're building, which looks awesome. Will it be flexible? Like you can run it with the mesh focused over Europe instead of the US, or are there things that kind of have to get hard coded that will make it most suitable for the US, and it'll be a lot of work to validate it for Europe?
Yeah, good question. So as we started these projects 2 years ago, there were a lot of issues in grid generating infrastructure at GFDR. So you were at GFDR, you know, we have to generate a grid with free software. And there were a lot of issues about that. And we were able to work with the modeling service team to fix some of the issue. And actually just a few weeks ago, we found some solution that we can create this stretch grid for anywhere, reasonable high quality stretch grid structure for anywhere in the world. We can focus on the US, and we can zoom into Europe, and we can zoom into China. So once the grid structure, you know, grid spec is created, then the model run on this grid. So the model are not specifically coded, you know, to run on a specific grid structure.
Cool. Thank you very much. That's exciting.
Thank you. So Elia said that she's gonna upload this seminar recording on the website sometime early next week. Any other questions? So about this your suggestion about long-term observation of ozone and then Biogeochemistry VOC, I think you are more specifically about flux instead of concentrations. Is that right?
Yes.
So concentration itself probably wouldn't help you too much.
Yes, because concentrations, we have those monitors from EPA. So
right.
I think we have, well, we never have enough data, but
right.
we have quite a lot of ozone concentration observations already.
Yeah.
So I'm thinking about flux measurements to be able
right.
to understand deposition velocities.
I think it seems like a CO2 has better success in terms of having network of long-term flux observation. I guess that's probably behind of it. There's commercial instrumentation out there. And then I guess DOE is more enthusiastic maintaining this network. And then probably it's been about 10, 15 years, maybe Alex said it's 20, 30 years. People just saying that we really need to have a long-term observational site. I think some people tried that in university, but never be able to maintain it because it is just tough in the university. And then even in the institution, I guess that's a research institution or common lab is not easy. I was wondering, is there any internal discussion at NOAA? They are talking about having this network or a couple of sites doing long-term observation of...
I have been advocating this
okay.
to different people, but such discussion are not in place. I mean,
and then maybe other question is that if it is too difficult, then do you think we can use concentration as a proxy? May not be perfect, but is there any way we can use concentration data to deduce flux out of it? If we could do that, will there be any additional data set that we will be needing or something? Maybe ozone is tough, I guess, but yeah.
Yeah, I'm not sure how to relate concentrations with flux.
Right.
But I think even long-term like ozone concentration observations are variable to evaluate model indirectly. As I show for Europe, I don't have long-term flux measurements, but seeing that accounting for this reduced ozone removal by drought stress vegetation, improve model simulations of ozone concentration on interannual to decadal time scale, I think that's a useful way to think about using those data and evaluate model indirectly.
Yeah. So speaking of that European study you conducted, so you attributed most of ozone increase to the reduction of the deposition, but so how about some other impacts from drought or heat wave, like accelerated chemical processes or the increased emission, things like that? Those
so that's all included.
Okay, they are all included. Okay.
Yeah. So for example, this blue line. So this model is driven by a change in
I see.
of the reductions in anthropogenic emissions.
Okay.
So and also the model is nudged to reanalysis on winds. So this stagnation is already included, and also isoprene emissions change is included in the blue line. So you could say that including all those factors already, the model still have difficulty simulating the observed ozone anomalies. Okay. And this orange and red line is additional to simulation to account for variabilities of ozone deposition.
Mm-hmm. Thank you very much. Any other questions?
I have a question.
Go ahead.
So just this figure, so about the 1994 and 2006. So when you simulate these 2 years about the ozone formation in the Europe, at that point or during that years, it's like NOx limitation, or it's like VOC limitation?
You mean these years, whether it's NOx limitation? I'm not sure. I think they both play a role during heat wave. Whether this is NOx, I'm not sure. I'm not sure. And it's difficult to judge whether this NOx limited or VOC limited.
Could it be possible? Sorry.
It depends on locations we are looking at, whether it's rural sites or urban sites.
Could it be possible that the NOx emission just decrease, and in the past it's kind of like VOC limitation with the decrease of the NOx emissions? And
so actually, as I show here, so both NOx, so this NOx emission trend and this is VOC emission trend. So both NOx and VOC emissions decrease substantially over Europe.
I see. Got you.
All right. I guess thanks for the discussion that we have so far, and then thanks for visiting us remotely, Meiyun. And then this was a great talk, and then we learned a lot. So if you have any follow-up question, I think there was an email that was shared in the presentation, and then so if you could, if you could send an email to Meiyun. So thank you very much for the great talk, and then you have a good evening, and then thanks for coming.
Yeah, thank you. Thank you for having me.